Go ahead.
I will say a few comments. Basically, the way it's been looking from the Park Service, we got an email from the state parks. Our permit basically is canceled all the way to end of June.
Yeah, I thought so.
So the earliest we will be able to continue activities will be in July, if that is the end of the state parks being closed. If not, it will continue.
I'm not seeing you, PJ. I'm just seeing me, Ekta, and one that says James iPad.
I don't have my camera turned on.
Pardon?
I don't have my camera turned on.
Oh, very good. Okay. All right.
So
yeah, I can introduce her and talk about the next two talks. And
yeah,
thank you.
Then we've been talking at the board about some way we can do city star parties with social distancing, but it is a little difficult.
I know it's a very, when people are looking at your telescope, it's a very, face contact, intimate thing.
Well, even if we have a line of people separated every 6 feet or so, they still come to the telescope. But
then their eyes are there and they're poking their eyes and noses, especially the children all over everything. I love it, but now might be different. I mean, now will be different.
And similarly, our scheduled Yosemite event was for July 4th weekend.
Yeah,
I haven't heard officially, but it's likely not going to happen at that time.
Well,
the last time I checked for Yosemite, they will reopen in the mid of August, not before.
It depends on what the state level decides as well.
I'll update on the Yosemite trip as I hear officially.
Yeah. So anyway, I just wanted to let the attendees know about our activities. So for now, we will be having more of these online lectures.
I know.
Possibly, maybe we can even do our board meeting, stream it to multiple platforms to see if anybody to let people know what we do at the club, at the organization level, even though we have nothing to plan for the next several months.
Do you have any way of knowing how many people might be observing this talk tonight?
I see 3 pages of...
Like a 51 in here.
We have over 50 people on this session. I can see that already.
Right now.
Hey, PJ, we have some people who are talking in the background but would like to be muted and are having a hard time muting. As a moderator, can you just mute everybody at this point? And
yeah, I believe that.
That would be great. And then maybe go through how you would want to handle questions so people can unmute.
Oh yeah.
Thank you. Thanks, guys. Okay, Mike, I think you're muted now. And I am also.
We have the Q&A at the end of the lecture. Ekta will explain how to get her attention and speak at the right time.
Yeah, I think we'll do that at the end just because it doesn't matter so much now.
So then, Linda, I'm done with announcements per se, as underwhelming as they were. So you can begin when introducing the next speakers and so on.
Are you saying begin now?
Yes, please.
Okay. So I hope we have some people listening tonight, watching tonight that are new and discovered us online. We always meet on the 3rd Wednesday of every month. On June 17th, the talk is called Sparkle in the Dark, the Outlandish Quest for Dark Matter. Maria Elena Monzani from Kavli Institute and SLAC National Accelerator Lab will give the lecture. The nature and origin of dark matter are among the most compelling of mysteries of modern science. For over 30 years, physicists have been trying to detect dark matter particles with little success. The next stage in the search is the LZ detector. It consists of 10 tons of liquefied xenon gas stored in a refrigerated titanium cylinder a mile underground and in a former gold mine. I think we'll find that a very interesting talk. July 15th, Wednesday, did comets jumpstart life on Earth? Matthew Kroonblad from the Lawrence Livermore National Lab will give that talk. Recent observations confirming the presence of protein-forming amino acid glycine in comets lend support to cometary impact as a possible source for delivering simple amino acids to the early Earth. Quantum-based molecular dynamics, QMD, are a useful modeling tool, and our studies help determine a feasible pathway toward chemicals needed for life on Earth. So those are the June and July talks. Ekta, are you ready soon?
I'm ready. Yeah.
All right. So our speaker tonight, I'm pleased to say, is Dr. Ekta Patel. She is a Miller Fellow in the Department of Astronomy at the University of California, Berkeley. She received her BA in physics from the New York University in 2014, and her PhD in astronomy and astrophysics from the University of Arizona in 2019. The University of Arizona's Steward Observatory, she worked to analyze high-resolution cosmological simulations to help us understand the dynamical history of our local group of galaxies. At UC Berkeley, she is continuing her work on understanding the dynamics of satellite galaxies orbiting the Milky Way and Andromeda. She's also engaged actively with the public in a variety of ways in her career so far, including past involvement with Colors of Nature, Project Astro, and the National Optical Astronomy Observatory Teen Astronomy Cafe. Satellite galaxies in the local group will be the topic tonight. Our local group of galaxies is composed of our Milky Way, Andromeda, and dozens of small satellite galaxies. Satellite galaxies are thought to be building blocks of more massive galaxies, so studying their histories is crucial to understanding how the Milky Way and Andromeda arrived at their present properties. Dr. Patel will explain how the orbital histories will help us learn about the evolution of these satellite galaxies themselves. And we heartily welcome Dr. Ekta Patel.
Thank you. And thanks, PJ, as well. I'm really happy to be here tonight. And like I said, I would love to have been in the museum with all of you, but alas, here we are. So hopefully this will do. I will explain at the end of the talk how we'll deal with questions and answers. There will be time to do that. Unfortunately, not if you're watching on YouTube or Facebook. But if you type into the chat during the talk, I likely won't see it just because my screen is covered with my slides. But maybe PJ, if there's something, or Linda, if there's something happening where you can't see my slides advanced or something like that, just unmute yourself and let me know.
Okay.
All right. Otherwise, I'm going to mute everyone now, and we'll get started. All right. Well, thanks for that nice introduction and that summary. I will be talking about all of the things that were mentioned today. And I'm glad that there's a talk on dark matter coming next, because I will also talk a little bit about dark matter, not quite how we're searching for it, but why it's relevant in the context of galaxies. And today I'll tell you a lot about what I've done, both in my dissertation work while I was at the University of Arizona, and also about the work that I'm continuing to do here while I'm at UC Berkeley. So we'll talk about satellite galaxies in the local group. And I'll come back to this image that you're looking at here and explain what you're seeing in just a few minutes. So for this talk, let's see if my clicker will actually advance. No, apparently not. All right. So for this talk, I would like to go through and answer, hopefully, at least in a short version, these two questions, which are what are satellite galaxies and why are they important? And how do astronomers use observations and simulations to study satellite galaxies? So I'll also touch a little bit on the history of this field, including topics like dark matter and the Milky Way. And near the end of the talk, I'll talk more about modern observational and computational techniques that astronomers like me are using in our everyday research to answer some questions like this. And to start, I just want to define a few of the key terms that you saw in my title, so that we're all on the same page moving forward. So first, I want to talk about not necessarily satellite galaxies, but in general, what is a galaxy? Typically, when we hear the word galaxy, we think of very pretty images that look like this. However, the definition of a galaxy and what that is has actually been changing even until very recently. And actually, we're coming up on a 100-year anniversary of something called the Great Debate, where two academics actually were debating whether the Milky Way galaxy, our own galaxy, was the entirety of the then known universe, or if it really just was one galaxy amongst a sea of many, which at that time galaxies were referred to often as spiral nebulae because people just didn't really know what exactly a galaxy was necessarily. But like I said, even now our definition is being updated. So likely when you hear the word galaxy these days, you think of images like this or this or this or this. There's a broad variety of images. But you might also wonder, well, why aren't these images characterized as galaxies, or are they? And so for this reason, a couple of astronomers just in the last decade actually took the time to sit down and come up with a way to really define a galaxy now that our picture of what the universe looks like is drastically changing as technology advances. And what they defined a galaxy to be is a galaxy is a gravitationally bound collection of stars whose properties cannot be explained by a combination of baryons and Newton's laws of gravity. Now that's a mouthful, so I'll break down a little bit of this. So by baryons, we're just talking about simple subatomic particles that you've probably heard of, like protons and neutrons. And by Newton's laws of gravity, if you took a high school level physics class, you might remember hearing force equals mass times acceleration, or that massive bodies feel equal and opposite forces. And that's what we're talking about when we think of Newton's laws of gravity. So essentially, this is the current definition of what a galaxy is. And what that really means at the end of the day is that if you cannot explain a galaxy by the combination of baryons and these laws of gravity, then you have to invoke something additional, some additional mass, gravitational mass, that interacts, again, in a gravitational sense with the other matter in the universe. And what we think that might be is dark matter. And so I'll talk a little bit more about dark matter in just a bit. So now that we know what a galaxy is, let's talk about what a satellite galaxy is. By the name, you may have a guess already as to what that really is. And I like to think of them analogous to the way that moons orbit around planets. We have a moon orbiting around our own Earth. In the same sense, satellite galaxies also orbit around another galaxy. And so the different definition for the sake of this talk is really just a galaxy that orbits a larger and more massive galaxy. And then finally, I like to define what we call the local group, which if you heard Linda's introduction, you already heard what exactly is in the local group, but I'd like to show you a bit of a schematic of what that looks like to scale. So first we have our own Milky Way galaxy, and then around it, you see many of these small bright points. And those are all what we're calling these satellite galaxies. So they're orbiting around our own Milky Way. And here you just see many of the labels of the names of these satellite galaxies. Some of them are more exciting than others. And in addition to the Milky Way and the dozens of satellite galaxies that are orbiting around it, our local group also consists of the Andromeda galaxy. If you have a Mac computer or have worked on a Mac desktop, you might have seen this Andromeda galaxy as one of the wallpapers that's available. But the Andromeda galaxy is the nearest, most massive spiral galaxy like our own Milky Way. And that's why these two galaxies and their constituent satellite galaxies are what we commonly refer to as the local group, because they really are the most local galaxies to us. And then lastly, the local group also consists of some isolated dwarf galaxies. So there are a few, if you can see my cursor here, there are a few sort of galaxies that are a bit further away in separation from either Andromeda or the Milky Way. And these two are also considered members of the local group, so they don't really appear to be gravitationally bound satellites of either the Andromeda galaxy or the Milky Way galaxy. So this is generally what we refer to as a local group, and this is where I do a lot of my work. This idea of satellite galaxies is not unique to our own local group. We do see satellite galaxies around other spiral and also elliptical galaxies out in the universe. So it's a very, very common phenomena, but the reason, of course, that I study them and why they're so exciting to me is that they are the closest and therefore we know the most about them, since they are the easiest to observe and understand. Just for some distance references, if you're up on your astronomer lingo of kiloparsecs or megaparsecs, I've listed in parentheses the distances here, but in light years, the Andromeda galaxy and Milky Way are separated by about 2.5 million light years. And this local group has a radius of about 3 million light years. And so that's generally what we refer to as this group of galaxies. Now, this image doesn't actually show you all of the satellite galaxies that we know of in the local group. It shows many of them, but it actually does not show all of them. And the reason for that is because it's just been in the last 5 to 6 years that many of these satellite galaxies around the Milky Way were discovered. And so here what I'm showing is a bit of a discovery timeline of these satellite galaxies. So on this bottom axis, you're seeing the year of discovery, where I've just limited this to the year 1700 up to present day. And on the vertical axis, you're seeing the cumulative number of satellites. And so you might notice that going back to 1700 and actually even way well beyond the year 1700, there are 2 known satellite galaxies that are essentially the most well-known and most famous satellite galaxies orbiting around the Milky Way, and those are the Large and Small Magellanic Clouds. So these have been known to humanity for many, many hundreds of years. They are actually visible from the southern skies. So if you've had the fortune of going down to the southern hemisphere in a dark place, you might have actually seen these sort of puffs of light in the sky. And I've outlined them here. This is the Large and the Small Magellanic Cloud. And so these have actually been known to humankind for very long. You can find them in literature from all different peoples from around the world if you look for them. So yeah, if you ever get a chance to go to the southern hemisphere and be in a dark place, please do look for them. I have not seen them myself actually yet. So these are the 2 most well-known satellites of the Milky Way, as I said. And then as you move forward in time, of course, we found more and more of these satellite galaxies, largely due to the fact that our technology has advanced as well. So as we approach the 1950s, you see there's this sort of blip that goes up to about 10 known satellite galaxies. Many of these were discovered in photographic plates. And then as you move towards the year 2000, you see a very, very sharp increase in the numbers of satellite galaxies that have been discovered around the Milky Way. These 2 more recent spikes, I'll call them, are due to 2 very large efforts. The first being something called the Sloan Digital Sky Survey, which is a survey that was taken with the Sloan Digital Sky Survey telescope at Apache Point in New Mexico. And what makes it a digital sky survey is that this telescope scanned the sky many, many hundreds of times in the northern hemisphere, covering many large swaths of the sky, such that we could see fainter and fainter objects, essentially meaning that they're further and further and even dimmer in the night sky. And so that was very, very helpful in finding many of these satellite galaxies, since they really are some of the hardest stellar systems to find. The second increase here, as we move even closer to present day over here, is largely due to something called the Dark Energy Survey, which, as you might guess by the name, is the main goal is to figure out what is dark energy, which I won't talk more about today. But this Dark Energy Survey is based in the southern hemisphere at Cerro Tololo, and that telescope is taking many images of the sky again, scanning multiple times over the same swaths of sky, so we can see deeper and deeper and fainter objects. But much of that survey is actually located in close proximity to where the Large and Small Magellanic Cloud are on the sky, which I'm showing here. And so this red outline is showing you just a portion of the survey area of the Dark Energy Survey. And all of these dots are actually highlighting many of the newer satellite galaxies that were discovered in just the last 10 years or so. So many of these satellites were discovered in the vicinity of these Large and Small Magellanic Clouds, which is already interesting in its own right, because there's an idea that potentially many of these satellites are even satellites of these galaxies, which is then a satellites of satellites hierarchy. And I will touch on that at the very end of my talk. Okay, so far I've told you about the modern definition of galaxies, what are satellite galaxies, and you might be wondering, well, okay, we know what satellite galaxies are, but why are we listening to a 45-minute long talk about them, and why are they important? So let's get into that. So the first reason is that satellite galaxies are essentially the building blocks of galaxies. So in the same way that plants need water to grow, satellite galaxies contribute to the growth of their host galaxies. And so in this image, which I also showed on my title slide, what you're seeing is a host galaxy, and this is an artist's depiction. So this galaxy is a spiral, and it looks maybe, what we think our Milky Way galaxy looks like. And what you're seeing in this sort of ribbon-like structure is a satellite galaxy that has orbited around this host galaxy a few times, and in doing so has lost many of its own stars to the gravity of this host galaxy that it's orbiting around. thereby forming this ribbon-like structure of stars, which we refer to as a stellar stream. And eventually what would happen, if you could see this picture sort of moving in time, is that this satellite galaxy will actually eventually fall towards the center of this host galaxy, and over a very long period of time will eventually merge into it, so that the two galaxies become one. And the stellar stream will still be left behind as a sort of remnant of that process, and we do see this in the sky. And so in this way, these satellite galaxies are fueling the growth of their host galaxies. And that's, again, why we like to study the galaxies that we see orbiting around the Milky Way, because we think in the future the same will happen to them. And also that in the past, many of these processes have also occurred, building the Milky Way up to what we see it as today. So we see the process of these galaxies merging together when we look up at the night skies. When we use the most powerful telescopes in the world to look out into the universe, we see this process in action. So these are all real images from the Hubble Space Telescope, the Heritage team. And what you're seeing is pairs of galaxies that are either in the midst of starting to merge with each other, or at the very bottom right, you're even seeing the two galaxies that have then become one, or what we think have become one. And so we can capture these this merging process in a variety of phases, as you're seeing here. But in these pictures, you're seeing many galaxies that are roughly the same mass. However, as I've sort of alluded to, these satellite galaxies are typically dwarf galaxies, which just means that they're much lower in mass than galaxies like our own Milky Way. So these satellites are only about 10% of the Milky Way's mass or less. So the Magellanic Clouds, being the most massive ones, are the ones that are around 10% the mass of the Milky Way's mass. But these other satellites, many of them are thousands or even millions of times smaller than the total mass of the Milky Way. So the pictures of this would look actually very different, but I don't have any here right now. Okay, so I want to show you next a simulation of this process in action by actually showing you a movie, which will hopefully play clearly for everybody. But what you'll see is the growth of a Milky Way mass galaxy. And so what you'll watch is actually a rendering of a simulation. So this is not real data, but simulated data that is the result of astronomers putting the physics that we know about galaxy formation and evolution into a computer code and allowing it to run and form what we think might be a galaxy in a computer sense. And so I will play that for you, and it will start at 8 billion years ago, and it'll count forward in time. There'll be a little counter here, and if you're familiar with the quantity redshift, you might recognize that. But we'll start at 8 billion years ago, and we'll move forward in time. And this is what we're calling our central Milky Way-like galaxy, and it's like the Milky Way in that it's roughly the same mass as the Milky Way, which is about 1 trillion times the mass of the sun. And what you'll see as time moves on is this process in action where satellite galaxies are falling towards this galaxy, sometimes orbiting around once, twice, multiple times. But in the process of doing that, they're ripped apart and sometimes even fully merge into this central galaxy you're seeing here. So I'll play that. And as you can see, there's some balls of light falling in that are representing the satellite galaxies, like there and there. Sometimes they just fly past, sometimes they fly directly into the middle. Oftentimes they're being sort of shredded apart. That last one was very large. And even at the end, you see there that this very massive satellite galaxy is merging into its host. So that's sort of the process that I'm talking about here, that these satellite galaxies are really fueling the growth of the galaxies that they're orbiting around. So that's what we think is happening with our Milky Way and the satellite population around it, and the same with the Andromeda galaxy as well. Okay, the second reason that we are interested in satellite galaxies and their remnants, by which I mean the stream of stars that I was referring to earlier, the stellar stream, these satellites and their remnants help us learn about their host galaxies as well. So not only are they interesting in their own right, as they are some of the most faint stellar systems in the universe, but they also do tell us a bit about the galaxies that they orbit around, especially when we can study many tens of them orbiting around a galaxy like the Milky Way simultaneously. So before we get into the details of what we do learn about the host galaxies from satellites, I just want to go over quickly the anatomy of a Milky Way-like galaxy. So you've probably seen images like these, where this is an artist's depiction again of the Milky Way, but it's based on real data. So by taking real data, we can sort of reconstruct what we think the anatomy of the Milky Way is. Here you can see the location of the sun in one of the spiral arms. And on the right, you're seeing the sort of edge-on view or side view of the galaxy. And so it looks pretty much like a pancake from the side, where there's a little bit of a bulge of stars in the center. Again, the sun is located roughly here, and we'll refer to this thin sheet of stars sort of as a disk of stars. So those are the basic components of the Milky Way galaxy. But there's one component that is actually very important, especially in the context of satellite galaxies and what we can learn from them, that I'm not showing here. And the reason I'm not showing here is a little bit obvious, and it's that it is dark matter, and we don't actually observe it when we look out into the universe. So in general, we think that galaxies live inside of dark matter halos. So in my very, very basic schematic here, you see again a bulge of a galaxy and a disk of a galaxy like the Milky Way if you were looking at it from the side view. And what I've drawn in here in this gray region circled by the yellow dots is a dark matter halo, which is absolutely not drawn to scale on this image. In reality, we think dark matter halos around a galaxy like the Milky Way are roughly 20 times larger in radius than the size of that disk. But dark matter, we think, is where about 85% of the mass of a galaxy lies. So most of the mass that makes up a galaxy is not in the stars, it's not in the gas or the dust or the material between the stars and the solar systems and those galaxies. But we think a majority of this matter is really, a majority of this mass is really in the dark matter that we can't see. I'll give you one quick anecdote as to why we think this is the case, why we think that dark matter must exist, especially in spiral galaxies like our own Milky Way. To do that, I'll show you a little bit of work that was done by somebody you may have heard of, Vera Rubin. And what Vera Rubin noticed when she was taking observations of galaxies is that if she looked at the speed of stars near the center of the galaxy and compared them to the speed of stars, let's say near the outskirts of the galaxy, you would expect that stars, as you move outwards away from the center of a galaxy, would decrease, that the rotation speed would decrease. And you can think of this as if you were looking at a pinwheel or like a ceiling fan. If there was a point on the end of the fan's blades compared to a point at the center of the fan's blades, they would move slower. But when Vera Rubin was looking at the rotation speed of galaxies, and she did this with many, many galaxies, not just one, instead of seeing that the speed of stars as you moved away from the center were slowly declining, she actually saw that they either sort of stayed the same or were increasing. And so that's what I'm showing here in this very basic graph, where on the bottom horizontal axis, you see the distance from the center of this galaxy in the background. And the vertical axis is showing you the rotation speed of those stars as you move out of this galaxy from the center, where here you see slow and here you see fast. And so here in yellow, you see what would be expected. Stars move faster and faster, and then eventually the decline as you move very far away and move away from the stars that we can actually observe. However, what you really observed was this sort of green light curve where stars are moving faster and faster, and as you get to a certain point, they sort of plateau. So rather than the stars near the outermost regions of this disk moving slower, they actually were moving at almost the same speed. And so in order to explain this gap where these expectations are again based on the basic laws of gravity, but the observations don't follow that, to explain this gap, Vera Rubin suggested that there must be some invisible massive matter in the outskirts of galaxies to explain this gap. So essentially that means that these dark matter halos, because we think they are so large and that galaxies live inside of them, this is why we think there is so much mass, because from rotation curve arguments like this one that Vera Rubin presented for the Triangulum galaxy in this picture and also many other galaxies, she was able to say that there's got to be something else here for these speeds to make sense. Okay, so that's just a quick aside as to why we think there might be dark matter. There are other lines of evidence pointing to dark matter as well, but I won't talk about them here. Hopefully you'll hear about them next time though. Okay, so back to satellite galaxies. So the reason that satellite galaxies can help us learn about their host galaxies is because they can help us figure out where that dark matter is, what the shape of it is, and what that halo looks like without actually being able to observe it. So here I'm going to play a quick animation for you that I've made. And you can ignore the sort of numbers all on these axes. They're not really important for the point of this talk. But again, I've showed you this sort of very basic depiction of the Milky Way in the center with a bulge and a disk. And I've sort of crudely drawn on a dark matter halo, where here I've represented it as spherical, but we don't actually know whether it is spherical. And what I'm going to do is play this movie forward in time And these little points, which are all representing satellite galaxies, real satellite galaxies that we have observed around the Milky Way, you're going to start seeing them move, because I'm going to start showing you what we think the orbits of these satellite galaxies look like. So we're going to start at about 3.5 billion years ago, which is a very long time. And we'll move forward to today, and you'll see what these orbital trajectories sort of look like in a very basic sense. So we're approaching now 3 billion years ago, and you see these satellites are sort of falling towards the Milky Way. There's a variety of shapes that you see. So some of them are more circular, some of them are more elliptical, some of them don't really form a closed shape. Some of them orbit around multiple times, especially some of the ones near the center. I'll just pause this when it gets to the end so you can see some of those more clearly. But there's a variety of things that you can observe in terms of the shapes and sizes and lengths of these orbits. And so that is how these satellite galaxies help us learn about their hosts, in that by learning about the orbital trajectories of these satellites, they teach us about, for example, what is the total mass of those dark matter halos that they're orbiting around, since we can't actually observe the dark matter directly. And what is the shape of that dark matter halo? Again, I've drawn here as a spherical shape. We don't know if it's more shaped like a football, if it looks more like a pickle shape. We don't know if it's completely irregular from sort of a regular shape that we think of in the everyday world. But this is something that my collaborators actually are working directly on. So this is the sort of second main reason why we're excited about satellite galaxies and what exactly we can learn from them. As you've probably realized by now in the videos I've shown you so far, these timescales are extremely long. These orbital timescales are a few billion years. So rather than the way we see the moon orbit around the Earth just once every month, these orbital timescales are of course very, very long. And so we can't actually look up into space and over time track the exact full orbital trajectories of these satellites, where by full, I mean that we can't watch in a human lifetime one satellite galaxy orbit completely around its host one time. It's just such a long time scale that we can't really see that. And of course, at least right now, there's no way to speed up time, so we can't observe that ourselves. So we have to get a little bit clever as to how we can figure out how to actually study these orbital trajectories. And so what I'd like to tell you for the next few minutes is how we actually come up with calculations of what these orbits look like, as I've shown you in this video. So these are real calculations. You would find them in a real astronomical journal, and it's in studies that I've worked on. But I'll tell you a bit about how we get to this point of coming up with these orbital trajectories and then using those to learn about those host galaxy properties, such as the dark matter halo and its shape and its mass. So first, I want to talk about how astronomers use observations to study satellite galaxies and their host galaxies, and then I'll move into simulations. So to begin with, in order to come up with the types of orbits that I showed you just in the last 2 slides, the information we need is something called a proper motion. So you may have heard of this. It is simply, in a technical sense, it's the angle that an object moves across the sky as a function of time. More simply put, that means that if you took an image of a star today and you took an image of a star in 10 years, if you have some background reference for it, such as a very, very distant galaxy, you can actually tell what the change in the motion was of the star over those 10 years. So that's the basic idea of how we get proper motions. But the reason why these are extremely interesting motions to be able to measure is that they actually tell us the information about how a satellite galaxy or stars in a satellite galaxy are moving in full 3-dimensional space. So we can tell how satellites and the stars in them are moving towards and away from us. We call this a line of sight velocity, by taking a spectrum of stars in that galaxy and using something called the Doppler shift. But essentially what that tells us, and you don't need to really understand how that process works, but what that method gives us is just how a star in a satellite is moving towards or away from us. But what we really need to actually understand the full orbits of those satellites as they're orbiting around their host galaxies is not just how the satellites are moving towards and away from us, but also how they're moving in the transverse direction, so across the sky in that sense. And that's where this proper motion measurement comes in. So I'm going to show you this next movie, which is going to show you how the proper motion of the Andromeda galaxy was measured. So again, the Milky Way is sort of twin galaxy that's within the local group. And you'll hopefully very quickly notice why this is an exciting measurement to be able to take. And that's because it's a very difficult measurement to establish. So in the bottom right, as this movie plays, just notice the timeline that will count forward in time. So I'll let this play. We're going to zoom into a field of stars. These are in the Andromeda galaxy. So the brightest white points are the stars in the Andromeda galaxy, and you see them drifting relative to the background galaxies and stars. So essentially everything that's in the distance is very, very far away, such that it essentially looks like it's fixed in space. And those brighter white points are the stars in the Andromeda galaxy. And there you can see them sort of drifting, and that's this proper motion being measured. Now, if you've noticed this bottom counter, it started, I'll put it back to the beginning. This counter starts in the year 2012, which is when this measurement was published. Oops, sorry. Let's see if that will play. There you go. That's when this measurement was published in the year 2012. And again, if you count up as these stars are drifting and you see this motion, it's counting all the way up to the year 26,112. Now, the reason it's counting up so high is that this measurement, or this proper motion, is incredibly small. And what I mean by that is if you like analogies, then measuring the Andromeda galaxy's proper motion is like watching human hair grow at the distance of the moon. So it's an incredibly, incredibly small measurement that is taken even with the best telescopes in the world, like the Hubble Space Telescope. And so being able to measure this is extremely challenging, but also exciting once it's actually measured, because that's how we get the full three-dimensional motion of a satellite as it's moving relative to us in our own galaxy, the Milky Way. So again, when I show you these orbits, essentially what I need to be able to actually come up with is this, or what each of these orbits will look like is what is the full three-dimensional velocity of that satellite galaxy, and that's what these proper motion measurements and these line of sight velocity measurements give us. Okay, so that's how you get to these satellite orbits, and that is all sort of fueled by observations of stars in these satellite galaxies. We can also look at simulations and use those to study satellite galaxies as well, especially because the timescales we're interested in are so long, on the order of billions of years, that of course we can't really see these satellites orbiting fully around their host galaxies in the human lifetime. So I'll describe just one particular type of simulations in the astronomical community. If you've seen many of these talks, you've probably heard many other folks talk about all different types of simulations to represent the birth of stars or star clusters, or how supernovae explode, or how black holes form and grow over time. And the types of simulations that I will tell you about, and the ones that are most useful for the type of work I do, are something called cosmological simulations. So cosmological simulations are essentially at the sort of most extreme end of astronomy simulations, in that they're the most large scale. Their general goal is to reproduce a large swath of the universe. And so that means that these simulations are essentially creating an entire mock universe, where there are galaxies, there is dark matter, there are stars, there is gas, and you can track the evolutions of all of these what we call particles, so gas particles or dark matter particles or star particles, and you can track the evolution of them as they form galaxies, as galaxies merge, as galaxies are disrupted and torn apart. All of those processes are essentially reproduced in these types of simulations. So that's why I say that they're sort of the largest scale, not because they just because they require the most computing time, but also because they represent sort of many of the features that we see out in the universe, rather than just one galaxy or the one star cluster at a time. So these are very, very large simulations. So here what I'm showing you is something we often refer to as the cosmic web. And so what it's essentially showing you is the density of dark matter in this mock universe. And you'll notice it probably looks sort of like a filamentary structure of maybe like neurons in your body. And what you're seeing here is these filaments connecting, and at the brightest points, you see these pink magenta peaks. And those are what we call nodes. And at those nodes are where we think the galaxies actually form. So remember that we think all galaxies live inside of dark matter halos. And so there's this huge cosmic web of dark matter, where there are some places where there are sort of voids and nothing was really, no galaxies are really forming. And then there's others sort of like the chunk at the center of this image, where you see these very bright points, and that's where galaxies and galaxy groups and clusters are forming. So here you're seeing a very, very large swath of the mock universe represented in just the dark matter here. I'll play this and you'll sort of see all of the structure moving. So the benefit of these cosmological simulations is not only do we get a reproduction of sort of a section of the universe as we think we see it today, but it also allows us to track these structures as a function of time. since it's all simulated data, we can actually store, what galaxies looked like 8 billion years ago in the simulation, and then follow them all the way forward in time to what they look like today. And so that video I showed you earlier of a Milky Way-like galaxy eating many different satellite galaxies essentially comes from simulations like this. Okay, that's a lot of information, and it might be hard to sort of wrap your head around what this really still means in terms of a cosmological simulation. So I'm going to break it down a bit further, and I like to explain simulations like these cosmological simulations by giving you the analogy of a recipe. So this recipe in particular starts with some ingredients, where in our case, the ingredients are a set of equations describing the growth of the universe from the Big Bang to today, an efficient code to implement the model. And efficiency is key here in that because these simulations require so much computing time, you want to make sure that you're using the most state-of-the-art techniques so that you're actually speeding up the way that your code is processed. You also have to think about things like the number of particles. So what is the resolution of these galaxies going to be? Is each galaxy going to be represented by one mass particle, or will it be represented by hundreds of thousands of mass particles? So those are all things that need to be decided. The spatial resolution, the size of the simulation are all relevant factors here. So, in other words, you could think about, do we want to reproduce one galaxy, 1,000 galaxies, tens of thousands of galaxies? Those are all things that sort of go into the beginning set of ingredients for these simulations. Next, you need your cooking tools, which in this case will be supercomputers. You can think of supercomputers as thousands of desktops, essentially in one. Then you need a set of directions, of course. And so in this case, we'll need answers to questions like, what is the physics of galaxy formation? How do stars form? How do galaxies merge? How do black holes contribute to the evolution of their galaxies that they live in? So we have information about all of the answers to these questions by looking out into the universe and actually taking real observations. And by forming some conclusions based on those results, we can then feed them into this sort of larger model of a simulated universe. Then, of course, you have to wait. So essentially, this means that your supercomputer will run for 13.8 billion simulated years, which is approximately the age of the universe. Of course, since you're using a computer, we don't actually have to wait a real set of 13.8 billion years. Otherwise, that would really defeat the purpose of making these simulations. But the benefit is that when you're using these supercomputers, this will take a lot less real time to compute these types of simulations. And finally, what you end up with is about 1,000 gigabytes of simulated galaxies and their surroundings, matching the general properties of the galaxies we actually observe when we look out into the universe. And so with that set of simulated data, you can then answer many more questions that one can't answer by just looking up at the sky and taking pictures with telescopes, like things regarding the satellite galaxies and their orbits, which are occurring on billions of years of timescales. So next I'm going to show you a movie of a simulation like this, a cosmological simulation, and particularly one of the simulations that I've worked with. And it'll hopefully give you a little bit better of an idea of how these directions all kind of go in one place, and a simulation is born out of it. So you'll see two different boxes. On the left side, you'll see the dark matter density of this simulation. And on the right side, you're seeing the same simulation, but instead of looking at the dark matter, you're seeing the gas. So generally, you see many similar structural features in the left and right. And this is moving forward in time, by the way. So it started at roughly the Big Bang, and you're moving towards today. And what you're seeing on the right side now is some little explosions are occurring. These are massive stars dying. The supernovae are exploding, and they're expelling gas into the vast expanse of the universe, or the smock universe, I should say. And in the left, you're starting to see these dark matter structures grow that I showed you earlier. So these sort of bright pink spots where galaxies are starting to form are becoming brighter and brighter because more galaxies and groups of galaxies are forming there. On the right side, you simultaneously see that more and more supernovae explosions are going off, expelling large amounts of gas across very vast scales in space. And eventually we're approaching today. So it's about 10.7 years since the Big Bang happened, and we're coming towards present day. So this is kind of roughly what is encompassed with these cosmological simulations. And if you read the little tagline at the bottom, the simulation was run on over 8,000 computer cores and took 19 million CPU hours. And just for fun, that's equivalent to one computer running for about 2,000 years. So you really do need these supercomputers. And I would like to mention that these cosmological level simulations, again, because they are sort of the largest scale simulations that we do in the astronomical community, they really take a large team of people and large numbers of funding sources and many different supercomputers to put things like this together. And so there's only a handful of these types of simulations that exist, again, just because they take so much time and effort to create. Okay, so hopefully I've given you a bit of an idea of what these cosmological simulations are like. And now I'd like to just spend the rest of the time telling you how I actually use those, combined with the observations I was telling you about previously, to actually study these satellite galaxies that I've told you about. So using these cosmological simulations, what I do with them is I look for mass analogs of the Milky Way. So as I mentioned earlier briefly, we think the Milky Way is about 1 trillion times the mass of the sun. And we can look into these simulations, which form a variety of galaxies from dwarf masses all the way to very, very massive galaxies, even more massive than the Milky Way, as well as groups like our local group. And I essentially select out all of the galaxies that are roughly around the mass of the Milky Way. These images here are actually simulated images. This is not real data. These are not taken with telescopes. These are just renderings of data that have come out of simulations like the cosmological simulation I showed you previously, which is called Illustris, by the way. So these are 5 examples of roughly Milky Way mass galaxies. And once I select a few hundred of them from the simulations, I then look for satellite galaxies around them, which I've circled here in little blue circles. So I look for these satellite galaxies, and in particular, I look for the most massive of those satellite galaxies, often the ones that are most similar to something like the Large Magellanic Cloud, which are about 10% of the mass of the host galaxy at the centers here. And I look for those around these Milky Way analogs. That essentially gives me a statistical sample of Milky Way-like galaxies with satellite galaxies orbiting around them. So rather than just the one system that we can see and observe right now when we look out into the night sky in our local group, rather I should say 2 systems, because there's also the Andromeda Galaxy and its satellites. These simulations give us the benefit of having many hundreds of Milky Way-like galaxies and many hundreds of satellite galaxies orbiting around each one of those Milky Way-like galaxies. And so once I have those 2 sets of data, both the observations, which tell us about the actual satellites orbiting around the Milky Way, as well as the simulated data, which tells us about the hundreds of Milky Way-like galaxies and the properties of the satellite galaxies orbiting around them in the simulation, we can use these 2 sets of information together to really start to address many interesting questions about satellite galaxies that are of interest right now in the astronomical community. So I'll just quickly go over a couple of those. Some of those include things like, what is the frequency of satellite galaxies around simulated Milky Way-like galaxies? Are we missing any satellites when we look out into the real universe compared to what we find in these simulations, or do we find roughly the right amount? Is the Milky Way and its satellite system common or rare? So is the number of satellite galaxies we see around the Milky Way roughly consistent with what we're finding in the simulations, or is there a big disparity there? Other questions that are interesting are the orbital properties, so the shapes of the orbits, the timescale until they merge, of local group satellite galaxies typical? So again, we can observe some of these quantities for the real satellite galaxies orbiting around the Milky Way and Andromeda, and we're curious to know whether they're actually typical in the sense of the entire universe. And then what do current orbital properties of satellite galaxies imply about the host galaxy's properties? So this is again going back to questions like, what is the shape and the mass of the dark matter halo of the Milky Way? And we can again use these simulated satellites to address whether the satellites we really see around the Milky Way are representative, and how that similarity or difference helps us learn about the Milky Way itself. So these are many questions that I've worked on through a variety of my projects. If you're interested in them, there's some press releases on my website that I'll put up at the end of this talk. But to end, I just want to give you one applicable case study of all of the things I've told you about today. So I'll talk about a satellite galaxy, I'll talk about its orbit, and I'll talk about the implications of what that orbit means. So this case study is going to be on the orbital history of the Triangulum galaxy, which is also commonly referred to as M33. This is related to the Andromeda Galaxy, which is often referred to as M31. So again, going back to the schematic, here is the Andromeda Galaxy, M31, and here is Triangulum, which is M33. So you can see even just by eye that these are roughly, they're not quite the same in mass, but this satellite galaxy is fairly massive relative to its host galaxy that it's orbiting around. So in one of my first projects in graduate school, I was curious about the orbit of this galaxy M33 because we do have a proper motion measurement for it, as well as its host galaxy Andromeda, which I'm just showing a different view of here on the right side. This image on the right is actually real data from an observational survey of this region around Andromeda and Triangulum. And what I want to point out is that around Triangulum, which I'm going to refer to as M33 from here on, you see that there's some debris here that's been outlined. And that debris is actually highlighting debris in the form of stars. So there appears to be this sort of irregular stellar structure in the outskirts. So you can't quite see it in this image, but it would be sort of in the outskirts of this image here. This stellar debris was identified around M33. So in addition to this very nice spiral-like structure, it also has these strange irregularities in a little bit further away from the center of the galaxy, which we do see out in the universe. This is not completely uncommon, but it is curious. And it begs the question, where did this stellar debris around M33 actually come from? So just based on sort of this basic picture of the fact that M33, we think, is orbiting around this larger Andromeda galaxy, the very sort of traditional explanation for where these stellar debris, or sometimes they're referred to as warps in the stars, come from. This was typically explained by the fact that this Triangulum galaxy M33 might have had a close passage around its host galaxy Andromeda about 3 billion years ago, and that this close interaction is what leads to the stars in M33 starting to be sort of stripped away from the center nucleus of that galaxy. So as I showed you very early on in some of the animations I showed, you saw satellite galaxies emerging into a host galaxy like the Milky Way. And as that was happening, many of the stars in those galaxies are sort of being shred away from that central body. So that's essentially the hypothesis that was put in place also for this system. So here I'm just showing a sort of basic orbital path of Triangulum, where at some point it did pass close by Andromeda, and maybe that is how it got that stellar debris. But as I alluded to just a minute ago, we actually do have proper motion measurements for this galaxy M33, which means that we can actually rigorously calculate the actual orbital history of that satellite galaxy. And by doing that, what we found is that it actually appears that M33 has never in the past been close to M31, like is shown in its blue trajectory, but rather it's actually only reached its closest position today, which is this separation shown here. It's only reached this separation, which is the closest distance it's ever reached today, meaning that it hasn't ever interacted with the Andromeda galaxy in the past. And therefore, the stellar debris that I just showed in this previous slide that's shown here can't be explained by an interaction between these two galaxies. So then that goes back to the original question, which was, well, how did M33 come to have this stellar debris in its outskirts? Why are these stars looking like they're sort of disturbed away from the main nucleus of that satellite galaxy? And through some more analysis, what we hypothesized is that M33, which is a satellite in itself, in that it's orbiting around the Andromeda galaxy, appears to potentially maybe have its own set of satellite galaxies, meaning that through interactions with these satellite galaxies, perhaps it came to have that disturbed stellar debris around its main stellar disk, because some of these satellites have either merged into this galaxy M33 or have closely interacted with it, such that they have led to some of those stars being sort of disturbed away from a regular spiral structure. So that's a really exciting avenue that I've been thinking about a lot, is that there are satellite galaxies that may be orbiting around satellite galaxies. I also touched on this very early in the talk, where I mentioned that we might think there are also satellite galaxies around the Magellanic Clouds, which are satellites of the Milky Way. And so that's sort of the future trajectory of what I'm thinking about. And hopefully that leaves you with some interesting questions that I will take now. So you can unmute yourself if you have a question, and let me just explain how we'll do that. So if you are signed in Zoom and you click on participants on the bottom tab, you should see an option to raise your hand potentially. If you don't, we can also take questions by just typing them in the chat, which I can see now. PJ or Linda, if you want to also help with facilitating questions, I'd be happy to have that help as well.
I guess my iPad's too small to see it. Can you hear me, Ekta?
I can hear you, and PJ, I'm going to unmute you as well.
So we have two questions.
Okay.
So you can read the chat.
Let's see if I can get to it. For some reason, my chat is not showing. Ah, there it is. Nope, that's also not the correct one. I'm going to stop sharing my screen just because I think that's preventing me from seeing the chat. Okay, I do see the two in the chat now. So I see the first one is, what determines a large globular cluster versus a small satellite galaxy? Distance, movement, that's a great question. So first, to answer that, I like to mention that the reason why our definition of a galaxy is somewhat constantly, or at least recently, changing is because of this question. We're not often quite sure how to tell the difference between a globular cluster and a satellite galaxy. And so the very basic definition that I think astronomers are currently going by is that we think satellite galaxies, because they are galaxies, have dark matter. And you can see that if you measure the velocities of the stars in those satellite galaxies, and you'll find a distinctly different value for those speeds of those stars in the satellite galaxies, compared to if you look at a globular cluster and you measure the speeds of those stars, they tend to be much lower on average. So that's sort of a dividing line between globular clusters and satellites, is that we think the satellites have dark matter, and therefore the speeds of the stars are much higher than the globular clusters, in a relative sense at least. So thank you, Francisco. Then I see a question. Oh, sorry, that was from Nick Canis. Then a question from Francisco. Can you explain how the proper motions can be used to probe the shape of the dark matter halo? Sure. So the proper motions are what allow us to calculate the orbital trajectories that I was showing in some of those animations. So essentially, if we know the proper motion, we know not only how a galaxy is moving towards and away from us, but also sort of in all full 3 dimensions. So the combination of both the proper motion and what I was calling a line of sight velocity, so the towards and away motion, those two things combined really tell us in a full 3D space how a satellite galaxy is moving. And since we know the distance to those galaxies typically, and we know the full 3D velocity, we can then calculate a satellite's orbit. And we refer sometimes to those orbits as tracing out the dark matter halo. And so in some of the animations I showed, where I showed orbits of many satellites simultaneously, you saw that they were sort of tracing out a shape that maybe didn't really look regular in a sense. I represented the halo as a sphere. But by looking at many of those orbits simultaneously, the shapes of the orbits sort of help us trace out where the dark matter is, since that is really what is controlling the gravity of the satellites and how the orbits of the satellites are moving. So hopefully that answers Francisco's question. Take one from Juliana. So if satellite galaxies can help map the dark matter halo around a host galaxy, and there are satellite galaxies of satellite galaxies, would these smaller galaxies also have their own dark matter halos, and to what precision would we be able to determine dark matter halo distribution using this method? That is a great question. That is absolutely a concern that we are thinking about actively. So yes, we do think that even if satellite galaxies have their own satellite galaxies, we do think those two also live in a dark matter halo. And yes, in a similar sense, we can also, let's use the Large Magellanic Cloud again for an example. So the Large Magellanic Cloud is the most massive satellite galaxy orbiting around the Milky Way. And so we think there are satellites also orbiting around the Magellanic Cloud. So those satellites could be used also to attempt to measure the halo shape and mass of the Large Magellanic Cloud, where additionally that whole group of satellites is also then being used to measure the overall shape and mass of the dark matter halo of the Milky Way. So the applications of these methods are applicable at sort of both hierarchies. So that's a really great question. That's true. Okay, there's a question from Jim. How does some of this data help us study the shape and distribution of the dark matter halo? So hopefully I've maybe started to answer that a bit by answering the last few questions. But yes, having some information about the orbits of these satellite galaxies, and not just 1 or 2 satellites, but we're really getting to the point where there are now 52 satellite galaxies we know of orbiting around the Milky Way. And so in a sense, if you think of how those satellites are all collectively moving around the Milky Way, more and more information about the movement of those satellites is helping us sort of distinguish what might be underlying at the center of that gravitational potential. So hopefully that answers that question a little bit better, but please feel free to write more if that's not. Can we yet trace multiple satellite galaxies of Milky Way-like galaxies in significant numbers to help make generalizations about these dark matter halos, or do we only have that about the Milky Way and Andromeda? Another really good question. No, we don't have this for many, many large samples of Milky Way-like galaxies. The ability to measure proper motions, as I mentioned, is really difficult to do because it's a small measurement. Right now, we only have proper motion measurements for, I think, about 40 of the Milky Way satellite galaxies of about 52, so we're doing pretty good there. However, around the Andromeda galaxy, we know of about 35 satellite galaxies, and there are only proper motion measurements published for 2 of them, and I'm actually working with one of my collaborators to publish another 2, hopefully in the next few weeks. So that'll be 4 out of 35 that we have proper motion measurements for. However, when you go further outside of our local group of galaxies, those proper motion measurements become even more difficult because the amount of time you have to wait between taking one set of images and the next set of images to measure the difference in the motion of those stars across the sky increases. So essentially, if you want to look at the proper motion of a satellite of a Milky Way-like galaxy, but that's 5 times further than the Andromeda galaxy, you would have to wait. I don't know the calculation off the top of my head. It's not 5 times longer. It's more than that. You'd have to wait probably tens and tens of years to get accurate proper motion measurements for those satellites. So in terms of proper motion measurements, our local group is really the best bet right now. But maybe in the future, if there is, a telescope that's maybe even more powerful than the Hubble Space Telescope in terms of the size of the mirror, but also has very good instrumentation aboard, then maybe in the future we'd be able to get proper motions of satellites around much more distant galaxies. Yeah. Okay. Let's see. We have another question that says, recent data has shown a relationship between supermassive black holes and galaxy size, indicating that supermassive black holes are, in a sense, driving galactic evolution. Do we have any data on intermediate mass black holes being present within these satellite galaxies? And if so, what role do they play in the evolution of these galaxies? Yeah, that's a really interesting one. I am not as familiar with this line of work just because I don't think about supermassive black holes myself very much. However, there are current teams looking for intermediate mass black holes in these satellite galaxies, which are, I will say, they're not necessarily looking for them in the actual satellite galaxies of Milky Way, but galaxies that are of similar masses. So these satellites around the Milky Way are typically dwarf galaxies, which just means that they're sort of the smallest galaxies we find in the universe. And so there are teams looking for intermediate mass black holes in dwarf galaxies, and some have been found. I think there's not a large enough sort of sample of those that have yet been discovered so far to say a lot about what role they play in galaxy evolution. That's a really active area of research as well. So I'd encourage you to look more about that. Another question says, do you track the proper motions of stars in the debris? Yeah, that is definitely something that's possible to do. We are, let's see, I am working with a team of people who is trying to potentially get the motions of stars in M33, the Triangulum Galaxy's debris, but others have also tried to look at this. So it is possible to get the proper motions, not only in debris coming sort of away from a satellite galaxy central body, but also of those stellar streams that I was showing that are the sort of ribbons of stars that come away from satellite galaxies as they start to disrupt. It is possible to get their proper motions, which again then tells us a little bit more about the orbits of those satellites and the stars that are being drawn away from them. Let's see. And PJ or Linda, just let me know when we're sort of running out of time. I will keep going otherwise. Any tentative conclusions about the shape and distribution of the Milky Way halo? Yes, so I've also worked on questions like what do we think is the precise mass of the Milky Way's halo? I said a few times throughout the talk that we think the Milky Way's mass is roughly 1 trillion times the mass of the sun. That is indeed true, though we're not very certain about that measurement. And that the reason why that quantity is important, even though it is so vastly large compared to what we think about on the Earth, is that the mass of a galaxy, or the total mass, including the dark matter of a galaxy, we think is very closely correlated with the number of satellite galaxies one would expect to find around that galaxy. And so if we are uncertain about the exact mass of the Milky Way, it's then hard to compare whether the satellite galaxies that have been discovered so far, so those 52 satellite galaxies we know of, it's hard to then compare that to simulations or models where we can say, well, if a galaxy is this mass, it probably has this many satellites. And so that's an area that's a very active area of work in terms of figuring out what is the exact mass of the Milky Way. So I'd still say around 1 trillion solar masses. We're getting to a place where we can say that to roughly within a 30% error bar. The shape, there are not as many sort of published results on this. Many people have focused on a more regular shape, by which I mean either a sphere or sort of like a flattened pancake shape for a halo, or more of a pancake turned on its side. But of course, there could be a totally irregular shape as well to these dark matter halos. And actually, some of my colleagues at the University of Arizona are working on figuring out the shape of the Milky Way's halo. And I would say in a very basic sense that they're finding that it's not any sort of regular shape, and actually that the shape changes as a function of distance from the center of the galaxy. So close to the center of the galaxy, they're finding it seems to be somewhat spherical, actually. But as you move further and further out away from the galaxy, it seems to be sort of lopsided and not really a shape I can describe or put a name to just yet. Okay, and then how are satellite galaxies repopulated as the central galaxy attracts and merges its satellites? Yeah, that's an interesting one. Part of that answer we don't know very well, right? Because if satellite galaxies have completely merged into a galaxy, it's sometimes hard to know that process has happened. Not all of them leave behind these beautiful stellar streams that can be observed. However, we do think that galaxies like the Milky Way will eventually continue to merge with other galaxies. And so, for example, in our own Milky Way's case, we think in some 4 or 5 billion years that the Milky Way and the Andromeda galaxies will actually collide with each other, which will be a very exciting event, though I'm not sure that we'll be around to see it happen. But when that happens, the Andromeda galaxy essentially is barreling towards the Milky Way with its population of satellite galaxies as well. And so these two galaxies with their satellites are moving towards each other. And so through sort of more large scale mergers like that, this sort of super Milky Way Andromeda galaxy that will come to be one day will essentially merge its satellite populations. And so that may be one way that galaxies sort of refuel their satellite populations, is by merging with other galaxies that also have satellites. But that's probably sort of the best answer I can give you as to what we think might happen there. I think that's, okay, one more question. Regarding a previous question, wouldn't the proper motion of stars in a globular cluster match that of the nearby stars in the galactic region of the cluster versus different values of proper motions for stars in a satellite galaxies compared to the parent galaxy? Yeah, that is definitely possible. The globular clusters are found within galaxies themselves, so it is possible that the proper motions of globular cluster stars are similar to the stars of the galaxies that they reside within, whereas satellite galaxies might be a little bit different. However, globular clusters can also reside within satellite galaxies. So I think it's a little bit difficult to say what you would expect in terms of the differences between the proper motions in the globular cluster versus the proper motions of a satellite. So I think it's a little bit easier to distinguish the two between this velocity argument of those that have dark matter, i.e. the satellite galaxies, would have higher velocities than the stars in the globular clusters. All right, let's see. Given the level of sophistication of some of your work and your satellite galaxies peers' efforts in satellite galaxy observations, have there been any ancillary or accidental discoveries by your team or your peers of astronomical interest that was not directly related to your work? I don't know if that's true for my own work or my own direct colleagues. However, sometimes in finding these satellite galaxies, it is a bit hard to really say whether it's a satellite, whether it's a globular cluster, or whether it's neither. It does take quite a few measurements to really confidently say it's one or the other of these. So yeah, I can't say that it's happened at any point in my work. But yeah, I think there have been other teams that have essentially taken a satellite galaxy that we thought was a satellite and demote it from not being a satellite galaxy anymore. So I guess that's sort of one example of it. And then let's see, Francisco, dark matter halo might be regularly shaped. Is it likely to be chunky, granular, rather than smooth, if this makes sense? Yes, we think that there's a possibility that it might not be smooth. Yeah, in the sense that there could be sort of lumpiness to the shape of the halo. Absolutely, yeah. And I think that's what some of my colleagues are finding. I think I've answered all the questions in the chat so far. So,
We appreciate it very, very much.
yeah, you're welcome.
So happy that you were able to talk with us tonight. And that simulation that you showed, the illustrious simulation, was quite extraordinary.
Thanks. Yeah, you can find the you can easily find their website and look more about that simulation. It's pretty. They've got really interesting movies and images, and you can read more about it as well.
Yeah, that was really amazing.
Thanks.
And we thank you for your efforts to speak to us tonight so very much.
Yeah, I didn't quite see an actual question from James. So if there is one, please do tell me.
Well, first of all, I wanted to thank you for your presentation. It was fascinating. My question really has to do with, I've read quite a bit about controversy, current modern controversies surrounding discussions about the reliance on computer simulations for deciding hard scientific questions. And so I'm just wondering to what, if any degree, it seems to me like I'm fascinated by the idea of your large-scale cosmological simulation, but it seems to me like of necessity you're taking a set of measurements that you have available that are compared with the timescale of the universe as a whole. In essence, they're snapshots. The entirety of human recorded history is a very thin snapshot on that cosmological timescale.
Right.
And so, to what degree, if any, I'm curious, do you worry that your reliance on a large-scale computer simulation like that might possibly be leading you astray?
Yeah, no, that's a good question. We do talk about this often within the community and within especially the theoretical astrophysics community. No, that's a very good point. I mean, we do have to make lots of assumptions that go into these simulations, and of course, all of the results that come out of them then rely on these assumptions being true, which we don't actually know. Yeah, so there's definitely sources of error. Some of them that we're much more familiar with understanding, such as things like numerical errors that are introduced that might be sort of, for example, there are instances where the kinematics of stars in a disky like a spiral-like galaxy, might have slightly higher values than what we actually observe in the universe. And there are, well understood reasons as to why some of those phenomena happen by actually just looking into the simulation details themselves and just comparing and contrasting between, different sets of simulated data. There are, of course, other ones that are much harder to come by and to, really quantify in a sense of how much they are affecting one exact result, right? So if I'm using the simulations to, for example, estimate the mass of the Milky Way, it's a bit harder to say, exactly what the very minute sort of, details or caveats that there might be with the simulations are. I do think we have a good idea of sort of what the large scale variations might be that are coming from the assumptions that are made. Because we can run sort of smaller scale simulations where we can sort of perturb the assumption, right? And test something else instead and check what the effect is and then try to understand it on a larger scale. So yeah, I mean, there's definitely sort of areas of concern that we can test and actually kind of try to quantify as to how much that might be changing our results. And then there are other areas where it's much harder to actually disentangle the effects of some of these complications and then actually put a number to how much that might be changing our answer. So, I mean, I think that's generally sort of, something that we always think about very often, and that like we have to move forward with creating in these new sets of simulations with all of this in mind. But yeah, I mean, it's definitely at the forefront of what we're talking about. And of course, I think that, these models are the best we can do. And so that's kind of the way I like to think about them, is that they of course require assumptions. They're sort of the best we can do in the absence of being able to fast forward and rewind actual time. But yeah, I mean, the conclusions that are made from them are definitely, I would say, potentially less strong than what we could say from exact observations. Although even observations have their own set of difficulties in terms of really taking data and then disentangling what it really means, right? So in that sense, there's sort of an analogous set of complications that are sometimes more or less well understood. So yeah, that's a great point. And yeah, all of our work, I think it's pretty well acknowledged within the community, but it's definitely important to continue to remind ourselves.
Well, thank you.
Yeah.
Thank you.
All right. Well, with that,
hello. Can anybody hear Frank?
Yes, can hear you, Frank.
Oh, okay. I tuned in late. I had some trouble figuring out this new technology, but I eventually got up on it. Initially, I was up on the AAA in New York, and thinking I was on the San Francisco. So I said, well, where's the meeting? Because they were just talking. There was about 6 of them. And they said, oh, there's no meeting today. So I says, well, that's strange. I know there's supposed to be one. But then it dawned on me that perhaps I got up on the wrong email. So, but anyway, I do have one question.
Sure.
When the Andromeda Galaxy coincides with the Milky Way, which is in the distant future, of course, I was wondering if the total mass would be enough to form a spherical galaxy similar to M87.
Mm-hmm.
And is that perhaps not enough mass for that? Or what would your idea be on that?
Yeah, so I'm not sure it's entirely correct to say that it's mass necessarily that controls what type of galaxy will form. But certainly there has been work on what will happen when these two spiral galaxies collide. And we do think that they will form a more elliptical, sort of spherical-like galaxy. So yeah, certainly they'll have, nearly twice as much as mass as each of them currently have when you add them together. And yeah, we think that the shape will be more of a sort of ball-like structure with no spiral arms eventually. But yeah, right. Pretty much what the story you said is correct, I think.
Okay, thank you.
Yeah. All right.
I just want to say, if anybody missed the beginning of the lecture, the video will be available in a few days on YouTube. I will trim out anything prior to Linda making her introduction. So it'll be roughly hour and 10 minutes.
We thank you so much.
Thank you.
For giving us this talk tonight. It was wonderfully illustrated, and I'm glad that people had wonderful questions too.
They were very good. Those are actually
thank you so much.
Questions I've gotten actually. All right. I will end the call now. I believe that will also end it for everyone else.
So thank you.
Thanks everyone for joining, and take care.
Thank you very much.